Time has always been humanity's most mysterious companion. It flows around us like an invisible river, carrying our moments from the vast unknown of the future into the settled realm of memory. We measure it, schedule by it, race against it, yet it remains fundamentally enigmatic. Tonight, we'll explore one of physics' most captivating puzzles. What happens when time itself becomes flexible, bendable, and perhaps even reversible? What strange paradoxes emerge when we imagine traveling backward through the very fabric of reality? Hi, I'm Luna, and if you find comfort in quiet curiosity, gentle science, and stories that drift like starlight, you're in just the right place. So wrap yourself in something warm, settle in, and if you'd like to hear more sleepy wonderings, feel free to like and subscribe because tonight, we're going to drift through the elegant mathematical poetry of time travel paradoxes, where Einstein's equations whisper of possibilities that stretch our understanding of cause and effect, past and future, into beautiful, impossible knots. Time travel isn't just the domain of science fiction anymore. It lives in the heart of our most sophisticated physical theories, wrapped in the elegant mathematics of general relativity and quantum mechanics. These equations don't just allow for time travel. In some interpretations, they practically insist upon it. Yet with these possibilities come paradoxes so profound that they've puzzled physicists for nearly a century. As we settle into this exploration together, imagine time not as the steady tick of a clock, but as a vast ocean with currents and tides, depths and shallows. In this ocean, our usual understanding of sequence and causality becomes fluid, dreamlike. The paradoxes we'll explore tonight are like whirlpools in this temporal sea, places where the normal flow of events curves back upon itself in ways that challenge everything we think we know about reality. To understand time travel paradoxes, we first need to gently unravel our intuitive understanding of time itself. In our everyday experience, time moves steadily forward, like a river flowing from mountain to sea. Each moment follows the last in perfect sequence, and the arrow of time points relentlessly toward tomorrow. But physics tells us a different story, one far more nuanced and strange. Albert Einstein's special theory of relativity, published in 1905, first revealed that time is not the universal constant we imagined. Instead, it's intimately connected to space, woven together into a four-dimensional fabric called spacetime. In this framework, time becomes elastic, stretching and compressing depending on how fast you're moving and how strong the gravitational fields around you might be. Picture two twins, one staying on Earth while the other travels to a distant star at nearly the speed of light. When the traveling twin returns, she finds that less time has passed for her than for her earthbound sister. This isn't science fiction. It's a measured, verified consequence of special relativity. Time itself has been different for each twin, flowing at different rates in their separate reference frames. This elasticity of time becomes even more pronounced when we consider Einstein's general theory of relativity, published a decade later. Here, massive objects like stars and black holes actually bend spacetime around them, creating what we experience as gravity. Near a black hole, time slows to a crawl compared to regions of weaker gravity. An observer falling toward the event horizon would experience time normally. But to someone watching from a safe distance, that falling observer would appear to slow down, their movements becoming more and more languid until they seem to freeze at the horizon's edge. These effects are real and measurable. GPS satellites orbiting Earth must account for the fact that time runs slightly faster in their weaker gravitational field than it does on the planet's surface. Without these relativistic corrections, the GPS system would accumulate errors of several miles per day. Time, it turns out, is far more flexible than our intuition suggests. But general relativity opens even stranger possibilities. The equations that describe how matter and energy curve spacetime don't just allow for time dilation. They permit solutions where the geometry of spacetime itself creates paths that loop back through time. These theoretical constructs, known as closed time-like curves, represent the mathematical possibility of genuine time travel to the past. Consider the Alcubierre drive, a theoretical propulsion system proposed by physicist Miguel Alcubierre in 1994. Rather than accelerating to faster-than-light speeds, which special relativity forbids, this hypothetical drive would contract spacetime in front of a spacecraft and expand it behind, creating a warp bubble that could carry the craft faster than light relative to distant observers, while the spacecraft itself never exceeds light speed in its local reference frame. Such a drive could, in principle, allow for journeys not just across vast distances, but potentially backward through time itself. The mathematics of general relativity also permits other exotic possibilities, traversable wormholes that could connect distant regions of spacetime, rotating cosmic strings that might allow for time loops, and even the theoretical time machines proposed by physicists like Frank Tipler and Ronald Mallet. Each of these scenarios emerges naturally from Einstein's equations, suggesting that time travel might not just be possible, but inevitable in certain extreme configurations of matter and energy. Yet with these possibilities come profound puzzles. If time travel to the past were possible, what would prevent paradoxes that seem to violate our basic understanding of cause and effect? This question has generated some of the most fascinating and mind-bending scenarios in theoretical physics. The most famous of all time travel paradoxes carries a somewhat grim name, the grandfather paradox. But don't let its traditional formulation disturb our peaceful exploration. Instead, let's consider a gentler version that captures the same essential logical puzzle. Imagine a time traveler who journeys backward to prevent a historical disaster, perhaps a library fire that destroyed countless irreplaceable books. Our well-meaning time traveler succeeds, saving the library and its precious collection. But here's the paradox. If the library never burned, what motivated the time traveler to make the journey in the first place? The very success of the mission eliminates the reason for undertaking it. This creates what logicians call a causal loop, a circular chain of cause and effect that seems to violate our understanding of how events unfold. In the traditional grandfather paradox, the time traveler's actions prevent their own birth. But the gentler library example captures the same essential problem. The effect precedes and prevents its own cause. Consider the layers of complexity hidden within this simple scenario. The time traveler must have grown up in a world where the library burned, gaining the knowledge and motivation necessary for their mission. But if they succeed, they create a timeline where the library never burned, a timeline where their younger self would grow up without that motivation, perhaps never becoming interested in time travel at all. The paradox deepens when we consider the implications for free will and determinism. If the time traveler arrives in the past with knowledge of future events, do they have the power to change those events? Or are they somehow constrained to act in ways that ensure consistency? The question touches on fundamental issues about the nature of causality and the relationship between past, present, and future. Some variations of the paradox are even more subtle. Consider the information paradox. A time traveler brings back the plans for a magnificent invention, perhaps a design for a perpetual motion machine that they found in a future museum. They give these plans to a brilliant engineer in the past, who builds the machine and eventually displays it in a museum, where it's later discovered by the time traveler. Where did the information originally come from? The plans exist in a closed loop with no apparent origin point. Or consider the Shakespeare paradox, named after a short story by science fiction writer Ray Bradbury. A literature professor travels back in time to meet William Shakespeare, only to discover that the historical Shakespeare was an illiterate actor who never wrote a single play. Dismayed, the professor dictates all of Shakespeare's works to him, ensuring that they're preserved for posterity. But this means Shakespeare didn't write Shakespeare's plays. The professor did. Yet the professor only knew the plays because they were attributed to Shakespeare in his own timeline. Who, then, was the true author? These paradoxes share a common structure. They create causal loops where effects seem to precede their causes, or where information exists without an ultimate source. They challenge our linear understanding of time and raise profound questions about the nature of reality itself. But perhaps most unsettling is what these paradoxes suggest about identity and consistency. If a time traveler can change the past, they might erase the very circumstances that created their own personality, memories, and motivations. They might return to a present where they're fundamentally different people, or where they never existed at all. The time traveler becomes a kind of ghost, a consciousness from a timeline that no longer exists, carrying memories of events that never happened. Yet within these paradoxes lies a strange beauty. They force us to question our most basic assumptions about how reality works, pushing us to consider possibilities that stretch far beyond our everyday experience. They suggest that time might be far more strange and wonderful than we ever imagined, with hidden structures and secret pathways that our linear perception can barely comprehend. As we drift deeper into the mysteries of time travel, we encounter one of physics' most elegant attempts to resolve these paradoxes: the many worlds interpretation of quantum mechanics. This theory, first proposed by physicist Hugh Everett III in 1957, offers a breathtaking vision of reality that might make time travel paradoxes disappear entirely. In the quantum world, particles exist in states of superposition, simultaneously occupying multiple positions or having multiple properties until the moment they're observed. The famous thought experiment of Schrödinger's cat illustrates this strangeness. A cat in a box is simultaneously alive and dead until someone opens the box to look. The act of observation somehow collapses these multiple possibilities into a single reality. But the many worlds interpretation suggests something even more extraordinary. Rather than collapsing into a single state, quantum systems actually branch into parallel universes, each corresponding to a different possible outcome. Every time a quantum event occurs, and quantum events happen countless times every second throughout the universe, reality splits into multiple parallel timelines. In some of these timelines, Schrödinger's cat is alive. In others, it's dead. Both possibilities are equally real, existing in separate but parallel branches of the universal wave function. This interpretation transforms our understanding of time travel paradoxes. When our gentle time traveler journeys back to save the library, they don't change their original timeline. They create a new branch of reality. In this new timeline, the library never burns, and the time traveler who grows up there has no motivation to travel back in time. But the original timeline continues to exist in parallel, complete with its burned library and its motivated time traveler. There's no paradox because there's no single, consistent timeline to violate. Picture reality as an enormous tree, with branches splitting off at every moment where different possibilities exist. Our time traveler begins on one branch, call it Timeline A, where the library burned. They travel backward along this branch and then step sideways onto a different branch, Timeline B, where their actions prevent the fire. Timeline A continues to exist with its original history intact, while Timeline B develops its own separate future. The time traveler has become an immigrant from one reality to another. This solution is elegant because it preserves both free will and consistency. The time traveler can make any choice they want upon arriving in the past, because each choice simply creates a new branch of reality. There's no constraint forcing them to act in predetermined ways, because their actions don't need to be consistent with a single timeline. Every possible choice they might make corresponds to some branch of the infinite tree of parallel worlds. The quantum approach also resolves the information paradox. When our literature professor travels back and dictates Shakespeare's plays to the historical Shakespeare, they're not creating a causal loop within a single timeline. Instead, they're transferring information from one branch of reality to another. In Timeline A, someone else originally wrote the plays, perhaps Shakespeare himself, or perhaps the plays emerged from some other creative process. In Timeline B, the professor becomes the play's ultimate source. The information exists in both timelines, but with different origins appropriate to each reality's history. Some physicists have proposed even more sophisticated quantum solutions. The Novikov self-consistency principle, developed by Russian physicist Igor Novikov, suggests that quantum effects might actively prevent paradoxes from occurring. According to this principle, the probability of events that would create paradoxes becomes zero. A time traveler trying to prevent their own birth would find themselves mysteriously unable to complete the action. Perhaps their gun would jam, or they would suddenly feel compelled to change their mind, or some other quantum coincidence would intervene. David Deutsch, a pioneer of quantum computation, has proposed that quantum mechanics naturally resolves time travel paradoxes through what he calls quantum consistency. In Deutsch's model, when a time traveler attempts to change the past, quantum effects ensure that the changes are exactly the right magnitude to create consistency between cause and effect. The universe, in essence, fine-tunes itself to avoid paradoxes through quantum mechanical processes. These quantum solutions paint a picture of reality that's both more complex and more forgiving than our classical intuitions suggest. Time travel doesn't break the universe, because the universe is already broken into countless parallel pieces, each consistent within itself, but independent of the others. The branching structure of quantum reality provides infinite room for all possible stories to play out simultaneously. Yet this solution comes with its own profound implications. If every possible action creates new branches of reality, then every choice you've ever made has been played out in countless variations across parallel timelines. There are versions of you that made every possible decision, lived every possible life, experienced every possible joy and sorrow. The you that exists in this timeline is just one facet of an infinite diamond of parallel selves scattered across the many worlds of quantum possibility. In this vision, time travel becomes not a violation of causality, but a natural consequence of the quantum structure of reality. We're all already time travelers, constantly branching into multiple futures with every quantum event. The classical time traveler with their machine is simply taking a more dramatic step across the already existing bridges between parallel worlds. Among the most subtle and philosophically intriguing of time travel paradoxes is the bootstrap paradox, sometimes called an ontological paradox or a causal loop. Unlike the grandfather paradox, which seems to create contradictions, the bootstrap paradox creates scenarios that are logically consistent but mysteriously self-causing. These paradoxes whisper of realities where effects become their own causes, where information and objects exist in closed loops without any ultimate origin. Let's explore this through a gentle example. Imagine a young physicist who, while cleaning out her grandmother's attic, discovers a weathered notebook filled with complex mathematical equations. The equations describe a method for building a time machine, but they're written in her grandmother's handwriting and dated 50 years ago. Intrigued, the physicist studies the equations, builds the time machine, and travels back in time to meet her grandmother as a young woman. During their conversations, she shares the equations with her grandmother, who carefully writes them down in a notebook. Where did the equations originally come from? The physicist learned them from her grandmother, who learned them from the physicist. The information exists in a perfect circle with no apparent starting point. The equations are their own cause and their own effect, existing in a closed, time-like curve that defies our usual understanding of how knowledge is created and transmitted. This paradox takes its name from the phrase, pulling oneself up by one's own bootstraps, an impossible feat that nonetheless describes the logical structure of these self-causing events. In a bootstrap paradox, an effect reaches backward through time to become its own cause, creating a stable loop that sustains itself across the temporal dimension. The philosophical implications are profound. In our normal understanding of causality, every effect must have a prior cause, and every piece of information must have an ultimate source. But bootstrap paradoxes suggest the possibility of causation without ultimate origins, information without initial creators. They point toward a universe where some events simply exist as self-contained loops in the fabric of spacetime. Consider another variation. A time traveler visits a museum and admires a beautiful painting. The placard identifies it as the work of an unknown artist from the 18th century. The time traveler is so moved by the painting that they travel back to that era and, unable to locate the supposed artist, create a perfect copy themselves, which eventually finds its way into the museum where they first discovered it. The painting painted itself across the centuries, existing in a closed loop of creation and inspiration. These scenarios raise fundamental questions about creativity, originality, and the nature of knowledge itself. If information can exist in closed loops without ultimate sources, what does this mean for human innovation and discovery? Are we truly creating new knowledge, or are we simply finding our place in vast causal loops that stretch across time? Some physicists and philosophers have suggested that bootstrap paradoxes might actually be essential features of a universe that permits time travel. Perhaps certain information and objects exist as fundamental structures in space-time, self-sustaining loops that are as basic to reality as particles and forces. In this view, the equations in our physicist's notebook aren't created by any human mind, but are instead eternal patterns woven into the temporal geometry of the universe. The bootstrap paradox also appears in more subtle forms. Consider the possibility that time travel technology itself might be the product of a bootstrap paradox. Perhaps the first time machine was built by engineers who received the plans from time travelers from the future, who had received the plans from engineers, who had received them from time travelers, in an infinite regress of technological transmission. The technology would exist without ever having been truly invented, a gift from the future to the past that makes its own existence possible. Even more intriguingly, some interpretations of quantum mechanics suggest that the universe itself might be the product of a cosmic bootstrap paradox. In certain models of quantum cosmology, the universe emerges from quantum fluctuations in spacetime. But these fluctuations require the existence of spacetime itself. The universe becomes self-creating, pulling itself into existence through its own quantum mechanical bootstrap. These ideas push us toward a radically different understanding of causation and existence. Instead of linear chains of cause and effect stretching back to some ultimate beginning, we might inhabit a reality of causal loops and self-sustaining structures, where some aspects of existence simply are, without requiring external explanation or ultimate origins. The beauty of bootstrap paradoxes lies in their peculiar stability. Unlike the grandfather paradox, which seems to create logical contradictions, bootstrap scenarios are entirely self-consistent. Every event in the loop has a clear cause, the previous event in the loop, and a clear effect, the next event in the loop. The only thing missing is an ultimate beginning, a first cause that starts the cycle. But perhaps, in a universe where time itself can curve back upon itself, the demand for ultimate beginnings is simply a prejudice of our linear temporal experience. In the quiet spaces between cause and effect, bootstrap paradoxes suggest the possibility of existence without ultimate explanation, knowledge without final sources, and effects that gently reach back through time to ensure their own causes. They paint a picture of reality as a tapestry of self-weaving threads, each loop supporting the others, in an infinite dance of self-creation across the dimensions of spacetime. While dramatic scenarios of traveling backward in time capture most of our attention, the more subtle paradoxes of time dilation offer their own gentle mysteries. These effects don't require exotic time machines or traversable wormholes. They emerge naturally from the well-established physics of special and general relativity, creating temporal puzzles that are both mathematically precise and philosophically profound. The foundation of these paradoxes lies in the relativity of simultaneity, one of Einstein's most counterintuitive insights. In our everyday experience, we imagine that now is a universal moment shared by all observers throughout the universe. If something happens on Earth at noon, we assume it's also noon at that same instant everywhere else, on Mars, in the Andromeda Galaxy, throughout the cosmos. But relativity reveals this to be an illusion. There is no universal now. What counts as simultaneous depends entirely on the observer's reference frame. Consider two observers, Alice, who remains at rest, and Bob, who travels past her at nearly the speed of light. From Alice's perspective, events that she considers simultaneous, say, two fireworks exploding at the same moment in her reference frame, are not simultaneous from Bob's perspective. Due to his high speed, Bob sees one firework explode before the other. This isn't an optical illusion or a limitation of measurement. It's a fundamental feature of spacetime geometry. The very concept of simultaneity becomes relative, observer-dependent. This relativity of simultaneity creates subtle paradoxes when we consider faster-than-light communication or travel. Imagine that Alice and Bob can exchange instantaneous messages, signals that travel infinitely fast from the sender's perspective. Alice sends a message to Bob at noon in her reference frame. Bob receives it instantly from his perspective, but due to the relativity of simultaneity, he receives it before Alice sent it, according to his frame of reference. If Bob immediately replies with an instantaneous message of his own, Alice might receive his reply before she sent her original message. The conversation violates causality, with effects preceding causes. This scenario, known as the tachyonic antitelephone, demonstrates why faster-than-light communication is problematic in a relativistic universe. Any method of instantaneous communication, whether through hypothetical tachyons, quantum entanglement, or wormhole networks, could potentially be used to send information backward in time, creating causal paradoxes. The paradoxes become even more subtle when we consider gravitational time dilation. Near massive objects, time passes more slowly relative to regions of weaker gravity. An observer near a black hole experiences time normally, but from the perspective of a distant observer, their clocks run slow. This creates fascinating scenarios where different observers disagree not just about when events occurred, but about their causal order. Imagine two observers, one orbiting close to a black hole where gravitational time dilation is strong, and another orbiting much farther away where the gravitational field is weaker. Due to the difference in gravitational potential, time passes more slowly for the inner observer. They might observe a sequence of events, say, 3 spacecraft arriving in a particular order, while the outer observer, watching the same events, sees them occur in a different sequence. The causal structure of events becomes observer-dependent, challenging our intuitive understanding of cause and effect. These relativistic effects create a subtle form of time travel that's constantly occurring around us. The GPS satellites orbiting Earth are effectively time travelers, their clocks running faster than identical clocks on the planet's surface due to the weaker gravitational field at orbital altitude. Over the course of a day, these satellites accumulate a time difference of about 38 microseconds relative to Earth's surface, a tiny but measurable journey into the future. Even more dramatically, particle accelerators routinely create time travelers in the form of high-speed particles. Muons created in cosmic ray collisions in the upper atmosphere should decay long before reaching the ground, given their short lifetimes. But because they're traveling at nearly the speed of light, time dilation extends their lives from our perspective, allowing them to reach Earth's surface. From the muons' perspective, their lifetimes are normal, but the atmosphere itself contracts along their direction of motion, reducing the distance they need to travel. Both perspectives are correct within their respective reference frames, but they describe the same physical events in different ways. These examples illustrate a profound truth about time in relativistic physics. There is no single, universal timeline that all observers share. Instead, each observer carries their own personal timeline through spacetime, and these timelines can diverge and converge in complex ways, depending on motion and gravity. Time becomes a local, personal experience rather than a universal backdrop against which events unfold. The philosophical implications ripple outward like waves in a temporal pond. If time itself is relative and observer-dependent, what does this mean for our understanding of existence and identity? Are the events of your life arranged in the same temporal order for all observers? Or might some distant observer see your birth after your death, your effects before your causes? The answer depends on the specific trajectories through spacetime, but the possibility itself challenges our deepest assumptions about the nature of reality. We imagine ourselves as following a single timeline from birth to death, but from a relativistic perspective, we're better understood as four-dimensional objects extended through spacetime, with different cross-sections visible to different observers, depending on their motion and position in gravitational fields. This leads us to a gentle paradox of identity. Which version of you is the real you? The version that exists in your own reference frame, aging at your personal rate through your personal timeline, or the version that exists in some other observer's frame, where your timeline might be stretched or compressed, your causal relationships rearranged by the geometry of spacetime? The answer, like so much in relativity, is that all versions are equally real and equally valid. You exist not as a single, definitive entity moving through universal time, but as a family of related objects spread across different reference frames, each experiencing their own local version of temporal flow. Time dilation doesn't just affect clocks and particles. It affects the very fabric of existence itself, weaving reality into a tapestry where every observer experiences their own unique cross-section of the universal now. the block universe, and the illusion of flow. As we drift deeper into the mysteries of time, we encounter one of physics' most profound and unsettling insights: the possibility that time doesn't actually flow at all. This perspective, known as the block universe or eternalism, emerges naturally from the mathematics of relativity and suggests that our experience of temporal passage, the feeling that we're moving from past through present toward future, might be nothing more than a persistent illusion. In the block universe view, all of spacetime exists as a single, four-dimensional structure. Past, present, and future are equally real, equally existent, spread out across the temporal dimension, much like east, west, north, and south are spread across the spatial dimensions. Just as we don't think that distant places are somehow less real than our current location, the block universe suggests that distant times are no less real than the present moment. This perspective emerges from the relativity of simultaneity we explored earlier. If there's no universal now, if different observers disagree about which events are simultaneous, then there's no objective sense in which any particular moment can be considered the present. All moments exist with equal reality, forming a single, static block of spacetime that contains the entire history and future of the universe. Picture a loaf of bread that represents all of spacetime. Each slice of the bread corresponds to a moment in time as experienced by a particular observer. When Alice, at rest, cuts the bread, her slices are parallel to each other, representing her consistent definition of simultaneity. But when Bob, traveling at high speed, cuts the same bread, his slices are tilted at an angle, representing his different notion of what events are simultaneous. Both sets of slices are equally valid, equally real, but they divide the same underlying spacetime in different ways. This view transforms our understanding of time travel paradoxes. If all moments exist eternally in the block universe, then time travel isn't about changing the past. It's about navigating to different regions of an already existing spacetime structure. The time traveler doesn't erase or overwrite past events. They simply visit them, like a tourist visiting a distant city. Consider our gentle time traveler who prevents the library fire. In the block universe view, both versions of events exist simultaneously: the timeline where the library burns and the timeline where it's saved. These aren't sequential realities where one replaces the other, but parallel structures within the eternal spacetime block. The time traveler navigates from one structure to another, but both continue to exist with equal reality. This perspective suggests a radically different understanding of causation and choice. If the future already exists as surely as the past, are our decisions predetermined? The block universe doesn't necessarily imply determinism. Quantum mechanics might still introduce genuine randomness into the structure of spacetime. But it does suggest that the outcomes of our choices already exist out there in the temporal dimension, waiting for us to discover them through the act of living. Yet within this apparently static picture, the block universe theory must somehow account for our undeniable experience of temporal flow. Why do we feel like we're moving through time if time is actually just another dimension of space? Various theories attempt to explain this puzzle. One possibility is that consciousness itself creates the illusion of flow. Perhaps the brain's process of storing and accessing memories naturally creates a sense of temporal direction. We remember the past, but not the future, creating an asymmetry in our experience that we interpret as the flow of time. The present moment might be nothing more than the boundary between memory and anticipation, the constantly shifting divide between what we know and what we expect. Another approach suggests that the flow of time is real, but local rather than universal. Instead of the entire universe flowing through time together, perhaps consciousness creates small eddies in the temporal stream. pockets of genuine becoming within the larger block of spacetime. These eddies would be responsible for our experience of the present moment and the passage of time, while the larger structure remains eternally static. The thermodynamic arrow of time offers yet another perspective. While the laws of physics are generally time-symmetric, they work equally well in both temporal directions. The second law of thermodynamics introduces a preferred direction through the increase of entropy. The universe started in a state of low entropy, high organization, and has been gradually evolving toward higher entropy, greater disorder, ever since. This thermodynamic arrow might create the psychological arrow of time, giving us a sense of temporal direction based on the universal trend toward disorder. But perhaps the most intriguing possibility is that the flow of time is neither universal nor illusory, but represents something more fundamental about the nature of reality itself. Some interpretations of quantum mechanics suggest that the future remains genuinely open until quantum events collapse the wave function, determining which possibilities become actualized. In this view, the block universe grows moment by moment as quantum processes transform possibilities into actualities, and our experience of temporal flow reflects our participation in this cosmic process of becoming. These ideas carry profound implications for the nature of existence and identity. If all moments of your life exist simultaneously in the block universe, then every version of you, from birth to death, is equally real and equally present. The child you were, the adult you are, and the elder you will become all coexist within the eternal structure of spacetime. Death becomes not an ending, but simply a boundary, like the edge of a map that doesn't imply the non-existence of the territory it describes. Time travel paradoxes take on new meaning in this context. The grandfather paradox becomes not a logical contradiction, but a question about navigation within an already existing structure. Can the block universe contain causal loops, regions where world lines curve back and intersect with themselves? The mathematics of general relativity suggests that such regions are possible, though they might require exotic forms of matter and energy that don't exist in our local region of spacetime. The block universe also transforms our understanding of free will and moral responsibility. If all our choices already exist as permanent features of spacetime, are we truly free to choose differently? The question becomes less about whether we could have chosen differently, and more about whether our choices are genuine aspects of who we are as four-dimensional beings extended through time. In this eternal perspective, time travel paradoxes become explorations of consistency rather than possibility. The question isn't whether we can change the past, but whether the structure of spacetime permits self-consistent causal loops. The universe becomes a vast, four-dimensional sculpture, where every curve and intersection must fit harmoniously with every other part, creating a single, beautiful, mathematically consistent whole. As our exploration of time travel continues its gentle drift through the landscape of physics, we encounter the strange quantum phenomena that might actually make time machines possible. At the heart of many time travel scenarios lies the need for exotic matter, substances with properties so unusual that they seem to violate our everyday understanding of energy and gravity. Yet quantum mechanics suggests that such matter might not only be possible, but inevitable in certain circumstances. The story begins with empty space itself, which quantum mechanics reveals to be far from empty. At the smallest scales, the vacuum churns with virtual particles, pairs of particles and antiparticles that spontaneously appear and annihilate each other in times so brief that they barely disturb the apparent calm of empty space. This quantum foam represents the irreducible activity of the vacuum, the lowest energy state that space can achieve, while still obeying the uncertainty principle of quantum mechanics. These virtual particles normally have no observable effects, but under certain conditions, they can be coaxed into creating measurable forces. The Casimir effect, first predicted by Dutch physicist Hendrik Casimir in 1948 and later confirmed by experiment, demonstrates this beautifully. When two uncharged metal plates are placed very close together in a vacuum, they experience a small but measurable attractive force. This force arises because the quantum vacuum between the plates can only support virtual particles with wavelengths that fit exactly between the surfaces. Outside the plates, virtual particles of all wavelengths can exist, creating a higher pressure that pushes the plates together. It's as if the plates are being pressed together by the invisible weight of nothing at all, or rather, by the difference between two different types of nothingness. The Casimir effect is remarkable because it demonstrates that quantum vacuum can exert negative pressure. In regions where the vacuum energy is suppressed, space itself pushes inward rather than outward. This negative pressure is associated with negative energy density, a form of exotic matter that has gravitational properties opposite to ordinary matter and energy. While normal matter and positive energy create gravity, the familiar force that pulls things together, negative energy would create anti-gravity, pushing things apart. More importantly for our purposes, negative energy could be used to stabilize the exotic space-time geometries required for time machines. Many time travel scenarios, from traversable wormholes to Alcubierre drives, require regions of negative energy density to prevent their collapse or to maintain their unusual causal properties. Consider a traversable wormhole, a hypothetical tunnel through spacetime that connects two distant regions of the universe. Such a structure would naturally tend to collapse due to its own gravitational field. Pinching closed faster than light could traverse it. But threads of exotic matter with negative energy density, woven through the wormhole's throat, could provide the antigravitational effect needed to keep it open. The exotic matter would create a kind of scaffolding in spacetime, holding the wormhole's geometry in place against the natural tendency toward collapse. The requirements are stringent. The exotic matter would need to violate what physicists call the null energy condition, the requirement that energy density should be non-negative along any light-like path through spacetime. Such violations are possible in quantum mechanics, but they're typically small and confined to microscopic scales. Creating the quantities of exotic matter needed for macroscopic time machines would require extraordinary technological capabilities that are far beyond anything we can currently imagine. Yet the Casimir effect offers a proof of principle. It shows that exotic matter with negative energy density can exist, at least on small scales and for brief periods. Researchers have explored various ways to amplify and manipulate these quantum effects, from using moving mirrors to squeeze the quantum vacuum, to employing rapidly accelerating electromagnetic fields to create temporary regions of negative energy density. The quantum inequalities discovered by physicists like Larry Ford and Thomas Roman place limits on how much negative energy can be accumulated and for how long it can be maintained. These inequalities suggest that while small amounts of negative energy can exist temporarily, the universe has built-in restrictions that prevent the large-scale violations of energy conditions that would be needed for macroscopic time machines. But quantum field theory in curved spacetime reveals even more exotic possibilities. When quantum fields interact with the curved geometry around massive objects like black holes, they can create phenomena that seem to defy our classical understanding of energy and information. The Hawking effect, discovered by Stephen Hawking in 1974, demonstrates how black holes can evaporate by emitting radiation, gradually losing mass over time. This process involves the creation of particle pairs near the event horizon, with one particle falling into the black hole while the other escapes to infinity. The escaping particles carry positive energy away from the black hole, while the infalling particles have negative energy relative to distant observers, causing the black hole's mass to decrease. This suggests that regions of spacetime with strong curvature can naturally generate exotic matter with negative energy density. Near the horizon of an evaporating black hole, quantum effects create a steady stream of negative energy flowing inward, balanced by positive energy flowing outward as Hawking radiation. These quantum processes in curved spacetime might provide the natural sources of exotic matter needed for time machine construction. Even more intriguingly, some theoretical models suggest that advanced civilizations might be able to manipulate quantum vacuum states to create controllable sources of exotic matter. The Alcubierre drive, while requiring enormous amounts of negative energy, might be made more feasible if the negative energy could be confined to thin shells or concentrated along specific geometric structures. Recent research has explored ways to reduce the exotic matter requirements for such drives, potentially bringing them within the realm of possibility for sufficiently advanced technology. The dance between quantum mechanics and general relativity in these exotic scenarios creates a delicate balance. The quantum vacuum wants to maintain certain energy conditions and conservation laws, while curved spacetime offers opportunities to bend and manipulate these quantum states in ways that might permit the temporary existence of exotic matter configurations. Perhaps most beautifully, these quantum effects suggest that the universe itself might be a kind of time machine, constantly creating and destroying virtual particles in brief causal loops that exist below the threshold of direct observation. The quantum vacuum becomes a seething ocean of temporal possibilities, with virtual particles flickering in and out of existence in patterns that might, under the right conditions, be amplified into macroscopic time travel phenomena. As we settle deeper into our exploration, we encounter perhaps the most mysterious aspect of time travel paradoxes: the role of consciousness itself. While physics provides the mathematical framework for understanding exotic spacetime geometries and causal loops, the question of how conscious observers would experience these phenomena remains largely unexplored territory, a gentle frontier where physics meets philosophy in the quietest hours of scientific inquiry. Consider the peculiar nature of memory in a time travel scenario. Our sense of personal identity depends heavily on the continuity of memory, the feeling that we are the same person who experienced yesterday's events and made yesterday's decisions. But what happens to this continuity when time travel enters the picture? If a time traveler prevents their own birth, do they retain memories of a timeline that no longer exists? Are they condemned to become a living ghost, carrying impossible memories of events that never happened? The question becomes even more subtle when we consider the many worlds interpretation we explored earlier. If time travel creates parallel timelines rather than changing a single history, then the time traveler's consciousness must somehow navigate between these different branches of reality. They would carry memories from timeline A while living in timeline B, becoming a kind of interdimensional immigrant with experiences that no other person in their new timeline could share or verify. This raises profound questions about the nature of consciousness itself. Is consciousness simply an emergent property of brain states, completely determined by the physical configuration of neurons and synapses? If so, then a time traveler who changes the past might return to find their own brain altered in ways that change their personality, memories, and very sense of self. They might become a different person entirely, with no memory of their time travel adventure or their original timeline. Alternatively, if consciousness possesses some degree of independence from its physical substrate, if there's something like a soul or a persistent observer that transcends purely material processes, then time travel might create even stranger scenarios. The consciousness might retain its memories and identity while inhabiting a brain and body that belong to a different timeline, creating an internal conflict between remembered experience and physical reality. Some interpretations of quantum mechanics suggest that consciousness plays a fundamental role in the collapse of quantum wave functions, transforming possibilities into actualities through the act of observation. If this is true, then conscious time travelers might have special responsibilities and capabilities. They might serve as agents of quantum collapse, determining which timeline becomes real through the choices they make and the observations they perform. The bootstrap paradox takes on new dimensions when we consider conscious experience. If information can exist in closed causal loops without ultimate origins, what about experiences, emotions, and insights? Could a time traveler have a profound realization or emotional breakthrough that inspires them to travel back in time and create the very circumstances that led to that realization? The consciousness would become self-creating, pulling its own enlightenment into existence through temporal loops. Dreams offer an intriguing analogy for understanding these temporal puzzles of consciousness. In dreams, we routinely experience impossible narratives, paradoxical situations, and nonlinear sequences of events. We meet people who are simultaneously themselves and someone else, visit places that transform from familiar to strange without notice, and experience emotions that seem to arise from nowhere and everywhere at once. Yet within the dream, these impossibilities seem perfectly natural and coherent. Perhaps consciousness naturally possesses the flexibility needed to navigate time travel paradoxes, just as our minds can construct coherent experiences from the fragmentary and illogical narratives of dreams. They might be able to integrate memories from multiple timelines, experiences of causal loops, and encounters with their own past or future selves. The very plasticity that allows us to adapt to changing circumstances might also allow us to adapt to changing temporal circumstances. The phenomenon of déjà vu hints at this temporal flexibility. Most people have experienced the strange feeling of having lived through a moment before, of encountering a situation that feels hauntingly familiar despite being objectively new. While neuroscience offers explanations in terms of memory processing errors and neural misfiring, the subjective experience remains mysterious. Could déjà vu be a glimpse of temporal loops, moments where our consciousness briefly encounters echoes from other timelines or other iterations of the same events? Time travel scenarios also raise questions about the continuity of consciousness across temporal journeys. If you travel backward in time, do you experience the journey as a continuous stream of consciousness? Or do you somehow jump instantaneously from one moment to another? The question parallels long-standing puzzles about personal identity and consciousness in normal circumstances. Are you the same person who went to sleep last night? Or are you a new consciousness that happens to have access to the memories of that previous person? Some theories suggest that consciousness might be distributed across multiple timelines simultaneously. In this view, what we experience as a single stream of consciousness might actually be the integration of experiences from parallel selves living in different branches of reality. time travel would simply make this normally hidden multiplicity more explicit, allowing conscious access to experiences from other timelines. The meditation traditions of various cultures have long explored states of consciousness that seem to transcend normal temporal limitations. Advanced practitioners report experiences of expanded awareness that encompasses past and future simultaneously. States where the usual flow of time seems suspended or reversed. These reports might offer clues about how consciousness naturally relates to time and how it might adapt to the exotic temporal scenarios envisioned by theoretical physics. Perhaps most intriguingly, some researchers have suggested that consciousness itself might be responsible for the apparent flow of time. If the passage of time is indeed an illusion created by the way consciousness processes information, then sufficiently advanced understanding of consciousness might lead to technologies for manipulating temporal perception directly. Rather than building machines to travel through time, we might learn to navigate time by modifying our own conscious processes. As we drift through these gentle speculations, we begin to see that time travel paradoxes are not just puzzles for physics, but fundamental questions about the nature of experience, identity, and awareness. They force us to examine our most basic assumptions about what it means to be conscious observers in a universe where time itself might be far more flexible and strange than our everyday experience suggests. In the end, perhaps the greatest paradox is that consciousness, this mysterious capacity for subjective experience that allows us to ponder time travel in the first place, might be the key to resolving all the other paradoxes. If consciousness can navigate the impossible narratives of dreams and integrate the contradictory experiences of waking life, it might possess an inherent flexibility that makes it naturally suited to the temporal loops and causal paradoxes of time travel scenarios. In the vast tapestry of general relativity, few concepts capture the imagination quite like wormholes, those hypothetical tunnels through space-time that could connect distant regions of the universe, or even different times. As we continue our gentle exploration through the landscape of temporal paradoxes, these exotic structures offer perhaps the most concrete pathway from theoretical possibility to practical time travel. Though they remain wrapped in layers of mathematical complexity and physical uncertainty, the concept of a wormhole emerges naturally from Einstein's field equations, which describe how matter and energy curve the fabric of spacetime. Just as a piece of paper can be folded so that two distant points nearly touch, spacetime might develop folds and shortcuts that dramatically reduce the effective distance between regions that appear far apart in normal space. A wormhole represents the ultimate expression of this idea, a tunnel that creates a shortcut not just through space, but potentially through time itself. Picture spacetime as a vast ocean, with our familiar three-dimensional universe floating on its surface like a thin membrane. A wormhole would be like a tube that dives beneath the surface, connecting two points on the membrane through the higher dimensional bulk of spacetime. A traveler could enter one mouth of the wormhole, journey through the tube, and emerge from the other mouth, having covered vast distances in relatively little time. But the implications become even more extraordinary when we consider that the two mouths of the wormhole might not just be separated in space, but also displaced in time. The mathematics of wormhole construction requires what physicists call exotic matter, substances with negative energy density that create gravitational repulsion rather than attraction. Without such exotic matter, a wormhole would collapse faster than light could traverse it, making it useless as a transportation system. But with the right kind of exotic matter threaded through its structure, a wormhole could remain stable indefinitely, providing a permanent bridge between distant regions of spacetime. The process of converting a spatial wormhole into a temporal one involves a delicate manipulation of relativity's effects. Imagine that one mouth of the wormhole is accelerated to near light speed, while the other remains stationary. Due to time dilation, time passes more slowly for the accelerated mouth. When the acceleration ends and the mouth is brought back to rest near its partner, the two mouths will be synchronized in space, but displaced in time. A traveler entering the previously accelerated mouth would emerge from the stationary mouth in the past, having completed a journey backward through time. The beauty of this scenario lies in its consistency with known physics. No laws are violated in the construction or operation of such a time machine. The exotic matter requirements, while enormous by current technological standards, don't violate any fundamental principles. The time dilation effects that create the temporal displacement are well-established consequences of special relativity. The resulting paradoxes emerge not from flawed physics, but from the profound implications of consistent physical law applied in extreme circumstances. But wormhole time machines create their own unique set of paradoxes and constraints. The most significant is the chronology protection conjecture proposed by Stephen Hawking. This hypothesis suggests that the universe has built-in mechanisms that prevent the formation of closed time-like curves, paths through spacetime that loop back to their own past. When a wormhole begins to develop time travel capabilities, quantum effects might build up and destroy the wormhole before it can be used for temporal journeys. The mechanism behind chronology protection involves the quantum vacuum fluctuations we explored earlier. As the wormhole approaches the configuration needed for time travel, quantum fields traveling through it begin to accumulate and amplify. These amplified quantum effects create a feedback loop that grows stronger as the wormhole gets closer to allowing time travel. In the limiting case where time travel becomes possible, the feedback becomes infinite, destroying the wormhole in a burst of quantum energy. This creates a fascinating tension between the permissiveness of general relativity and the constraints of quantum mechanics. Classical relativity allows wormhole time machines, but quantum effects might always intervene to prevent their operation. The universe appears to possess a kind of immune system against temporal paradoxes, automatically destroying any structure that might permit causality violations. Yet some researchers have found ways to circumvent chronology protection, at least in principle, by carefully engineering the quantum vacuum states around a wormhole. It might be possible to suppress the dangerous feedback effects that would normally destroy the structure. These approaches require extraordinary precision and control over quantum fields, but they suggest that chronology protection might not be absolute. The engineering challenges of wormhole construction stretch far beyond current technological capabilities. The exotic matter requirements alone would demand the manipulation of quantum vacuum states on scales that dwarf any current human technology. Creating even microscopic amounts of exotic matter requires energies comparable to those found in particle accelerators, while macroscopic wormholes would need exotic matter in planetary quantities. But perhaps more interesting than the practical challenges are the theoretical implications. Wormhole time machines would create a universe where causality becomes negotiable, where effects can precede their causes, and where the very notion of temporal sequence loses its absolute meaning. They represent the ultimate expression of time travel paradoxes made manifest in physical structures. Consider the philosophical implications of a universe laced with wormhole networks. Different regions of spacetime could be connected by shortcuts that create complex temporal relationships. An action taken on Earth might cause an effect in the Andromeda galaxy that propagates backward through time to influence events in Earth's past. The causal structure of the universe would become a tangled web of forward and backward connections, creating a cosmic neural network where information and influence flow in all temporal directions. Some cosmological models suggest that the early universe might have been naturally rich in wormholes, created by quantum fluctuations in the primordial spacetime foam. As the universe expanded and cooled, most of these wormholes would have collapsed or become microscopic, but some might have been stabilized by exotic matter created in the high-energy environment of the early cosmos. These primordial wormholes could still exist today, hidden in the structure of spacetime, waiting for advanced civilizations to discover and utilize them. The possibility of natural wormholes raises intriguing questions about the history and future of life in the universe. Could advanced civilizations use wormhole networks for rapid transportation and communication across cosmic distances? Might such networks already exist, connecting intelligent species in a galactic community that remains invisible to us because we haven't yet learned to detect or access the wormhole connections? Even more speculatively, wormholes might play a role in the evolution of consciousness itself. If information can travel backward through time via wormhole connections, then the future development of intelligence might influence its own past emergence. The universe could become self-creating, not just in terms of physical structures, but in terms of the consciousness that observes and understands it. As we float through these possibilities like gentle explorers in a sea of spacetime, wormholes represent both the ultimate achievement and the ultimate challenge of time travel physics. They offer a pathway from pure theory to potential practice, from mathematical speculation to engineerable reality. Yet they also embody all the paradoxes and puzzles that make time travel such a fascinating frontier of physics and philosophy. In the end, wormholes remind us that the universe is far stranger and more permissive than our everyday experience suggests. They exist in the mathematical heart of our best physical theories, neither forbidden by known laws nor easily dismissed as mere fantasy. They represent possibilities that stretch our understanding to its limits, inviting us to imagine realities where the very structure of space and time becomes a technology waiting to be discovered and explored. As our gentle journey through time travel paradoxes continues, we encounter one of the most subtle and philosophically profound puzzles: the information paradox. This challenge strikes at the heart of how knowledge, experience, and information itself behaves in a universe where temporal loops and causal reversals become possible. It whispers questions that reach far beyond physics into the nature of creativity, discovery, and the very foundations of what it means to know something. The information paradox manifests most clearly in scenarios where knowledge travels backward through time without an apparent origin. Imagine a brilliant composer who, while exploring her grandmother's belongings, discovers a stunning musical score written in her grandmother's hand decades before she was born. Deeply moved by the composition, she decides to premiere it at a major concert. Years later, inspired by her success with the piece, she travels back in time and shares the score with her young grandmother, who carefully preserves it for the future. The music exists in a perfect loop. The composer learned it from her grandmother, who learned it from the composer. But where did the composition truly originate? This scenario captures the essence of information paradoxes. They create closed loops where information appears to exist without ultimate authorship, without a moment of genuine creation. The musical score possesses all the complexity and beauty of great art, yet it seems to have emerged from nowhere, bootstrap creating itself across the generations through the mechanism of time travel. The puzzle deepens when we consider the nature of information itself. In our normal understanding, information must be created through some process: observation, calculation, experimentation, inspiration, or conscious thought. Even apparently random information has sources: thermal noise, quantum fluctuations, or chaotic processes that generate complexity through natural mechanisms. But in temporal loops, information can exist in a steady state, neither created nor destroyed, but simply cycling endlessly through time. Consider the mathematical implications. Information theory, developed by Claude Shannon in the 1940s, provides precise ways to measure the complexity and content of information. A symphony, a novel, or a scientific equation can be assigned a specific information content based on the patterns and structures it contains. But if this information exists in a closed temporal loop, it seems to violate our understanding of how complexity emerges in the universe. The second law of thermodynamics tells us that entropy, roughly speaking, disorder or randomness, always increases in closed systems. Yet information paradoxes seem to create pockets where complex, organized information maintains itself indefinitely, without any input of energy or intelligence. The musical score in our example contains centuries of accumulated cultural knowledge, aesthetic insight, and creative inspiration. Yet it persists in its loop, without any obvious source of the organization it embodies. Some researchers have suggested that information paradoxes might be resolved through quantum mechanical effects. In quantum mechanics, information has peculiar properties that differ significantly from classical information. Quantum information can be in superposition states, existing in multiple configurations simultaneously until it's measured or observed. Perhaps information traveling through temporal loops exists in quantum superposition, containing multiple potential histories and origins until the loop is closed and a consistent history is selected. The quantum approach also suggests that information in temporal loops might not be truly static, but constantly fluctuating and evolving through quantum processes. The musical score might exist not as a fixed, unchanging entity, but as a quantum superposition of all possible scores that could sustain themselves in such a loop. The version that actually circulates through time would be the one that achieves quantum mechanical consistency across all iterations of the loop. But information paradoxes extend beyond simple examples like musical scores or literary works. They encompass entire worldviews, scientific theories, and philosophical insights. Consider a time traveler who brings back advanced knowledge of physics, perhaps the theory of everything that unifies quantum mechanics and general relativity. They share this knowledge with past scientists, who develop it further and eventually produce the very time travel technology that enabled the original journey. The theory becomes self-causing, pulling itself into existence through its own implications. This scenario raises profound questions about the nature of scientific discovery. Is knowledge something we create through our investigations and insights, or something we discover as an existing feature of reality? Information paradoxes suggest a third possibility: that some knowledge might be self-creating, existing in temporal loops that bootstrap themselves into reality through the very act of being known and applied. The philosophical implications ripple outward like waves in a pond of pure thought. If information can exist without ultimate origins, what does this mean for concepts like authorship, creativity, and intellectual property? Could Shakespeare's plays exist in temporal loops, cycling through history without a true author? Could scientific discoveries like the laws of thermodynamics or the principles of evolution be self-sustaining information structures that created themselves through time travel scenarios? These questions touch on deep issues in the philosophy of mind and consciousness. Human creativity often feels like a process of discovery rather than invention. Artists and scientists frequently report that their best ideas come to them fully formed, as if they were finding something that already existed rather than creating something new. Could this subjective experience reflect an objective reality where some ideas exist as timeless structures in the information landscape of the universe? The many worlds interpretation of quantum mechanics offers another perspective on information paradoxes. If every possible timeline exists in parallel, then perhaps information doesn't travel through temporal loops within a single timeline, but rather flows between different branches of reality. The musical score might originate in timeline A through conventional creative processes, then be carried by time travelers to timeline B, where it becomes part of a causal loop. The information has a genuine origin, but in a different branch of the multiverse than the one where the loop exists. This solution preserves the principle that information must have genuine sources, while allowing for the apparent paradoxes we observe in any single timeline. From the perspective of observers within timeline B, the musical score appears to be self-creating. But from the broader perspective of the multiverse, it has legitimate origins in timeline A. The paradox resolves into a more complex but consistent picture of information flow across multiple realities. Recent developments in quantum information theory have revealed even stranger possibilities. Quantum entanglement allows information to be correlated across vast distances instantaneously, suggesting that information might have non-local properties that transcend our usual understanding of spatial and temporal relationships. If information can be quantum entangled across space, perhaps it can also be entangled across time, creating temporal correlations that appear paradoxical from a classical perspective, but make perfect sense in quantum terms. These quantum approaches to information paradoxes suggest that our classical intuitions about information, causality, and temporal relationships might be fundamentally limited, just as quantum mechanics revealed that matter and energy behave in ways that violate classical expectations. The study of information in temporal loops might reveal new principles governing how knowledge and complexity propagate through spacetime. The resolution of information paradoxes might require us to develop entirely new frameworks for understanding the relationship between mind and reality, between the knower and the known. Perhaps information is not simply a human construct for describing patterns in nature, but a fundamental feature of reality itself, something that can exist independently of observers and participate in the causal structure of the universe in ways we're only beginning to understand. As we drift deeper into these gentle mysteries, information paradoxes remind us that knowledge itself is far stranger and more mysterious than we typically assume. They suggest that the boundary between discovery and creation, between finding and inventing, might be more fluid than we imagine. In a universe where time can fold back upon itself, the very foundations of how we understand learning, creativity, and the growth of human knowledge come up for reconsideration. As we continue our peaceful exploration through the landscape of temporal paradoxes, we encounter one of the most fundamental aspects of time itself, its apparent direction. While the laws of physics are generally time-symmetric, working equally well forward and backward, our everyday experience reveals a universe with a clear temporal arrow pointing from past toward future. This arrow manifests in countless ways. Ice melts into water, but water doesn't spontaneously freeze. Eggs fall and break, but broken eggs don't reassemble themselves. And memories flow from past experiences toward present awareness, but never in reverse. The source of this temporal asymmetry lies in the second law of thermodynamics, which states that the entropy of an isolated system always increases over time. Entropy, roughly speaking, measures the degree of disorder or randomness in a system. A pristine ice cube has low entropy. Its water molecules are arranged in an orderly crystalline structure. When the ice melts, the resulting water has higher entropy. The molecules move randomly in all directions, with no overall pattern or organization. This entropic arrow of time creates a profound backdrop against which all time travel scenarios must be understood. If time travelers could journey backward to periods of lower entropy, they would find themselves in a universe that appears to be running in reverse from a thermodynamic perspective. Hot objects would spontaneously cool by radiating energy into already warm environments. Gases would spontaneously compress into smaller volumes. Complex systems would spontaneously organize themselves into more orderly configurations. The implications for time travel paradoxes are subtle but profound. Consider our familiar scenario of the time traveler who prevents a library fire. In thermodynamic terms, the fire represents a dramatic increase in entropy. The organized structure of books and building materials transforms into the disordered hot gases and ash of combustion. By preventing the fire, the time traveler maintains the library in its original low-entropy state, seemingly violating the second law of thermodynamics on a local scale. But the thermodynamic analysis becomes more complex when we consider the broader context. The time traveler's journey itself requires enormous amounts of energy and inevitably produces entropy through the operation of their time machine. The prevention of one entropic increase might be balanced by larger entropic increases elsewhere in the system. The universe as a whole could still satisfy the second law, even while local pockets experience apparent reversals. This raises fascinating questions about the relationship between information, entropy, and temporal paradoxes. In 1961, physicist Rolf Landor demonstrated that erasing information always produces entropy, establishing a fundamental connection between computation and thermodynamics. If time travel scenarios involve the creation or destruction of information through the resolution of paradoxes or the establishment of causal loops, they must also involve corresponding changes in the universe's total entropy. Consider the information paradox we explored earlier, where a musical composition exists in a closed temporal loop without apparent origin. From an information theoretic perspective, the score contains a specific amount of complexity and organization. If this information truly emerged from nothing, it would represent a decrease in the universe's total entropy, seemingly violating the second law of thermodynamics. But if the information has quantum mechanical origins, spread across multiple timelines, or emerging from vacuum fluctuations, the entropic accounting becomes more subtle. The many worlds interpretation offers one resolution to these thermodynamic puzzles. If time travel creates new timelines rather than altering existing ones, then each timeline can maintain its own entropic arrow without violating the second law. The time traveler carries information from a high-entropy future to a lower-entropy past, but they do so by branching into a new timeline rather than reversing the entropy of their original timeline. The multiverse as a whole continues to increase in entropy even while individual timelines experience apparent reversals. But the relationship between entropy and time becomes even more mysterious when we consider the deep structure of spacetime itself. Some researchers have suggested that the arrow of time might not be fundamental, but rather emergent from the boundary conditions of the universe. The universe began in a state of extraordinarily low entropy, a highly organized configuration that has been evolving toward higher entropy ever since. This initial condition, sometimes called the past hypothesis, explains why we observe entropy increasing toward the future rather than the past. If the arrow of time is indeed emergent from initial conditions rather than fundamental to the laws of physics, then regions of spacetime with different boundary conditions might experience different temporal arrows. Near closed time-like curves, or in the vicinity of time machines, the usual relationship between entropy and temporal direction might break down entirely. Time travelers might encounter regions where entropy decreases toward what they consider the future, creating pockets of reverse causality embedded within the normal flow of time. The implications extend to biological and psychological processes as well. Living organisms are highly organized structures that maintain their low entropy states by consuming energy and producing waste heat. Consciousness itself might depend on this process of entropy production. The brain's information processing requires energy consumption and generates heat as a byproduct. In regions where the arrow of time is reversed or disrupted, biological processes might function differently or cease entirely. This creates additional constraints on time travel scenarios. A time traveler journey to a region where entropy decreases toward the future would find themselves in an environment where normal biological processes are impossible. They might need special protection or life support systems that can function independently of the local thermodynamic arrow. Alternatively, the act of time travel might automatically ensure that travelers always encounter regions where the thermodynamic and causal arrows align with their biological needs. Recent research in quantum thermodynamics has revealed even more subtle connections between information, entropy, and temporal relationships. Quantum systems can exhibit negative heat capacities, where adding energy actually decreases temperature. They can also experience quantum coherence effects that create correlations between past and future states in ways that classical thermodynamics cannot account for. These quantum thermodynamic effects might play crucial roles in the operation of time machines and the resolution of temporal paradoxes. The study of black hole thermodynamics has revealed particularly profound connections between entropy, information, and time. Black holes possess entropy proportional to their surface area rather than their volume, suggesting that information about their contents is somehow encoded on their boundaries. As black holes evaporate through Hawking radiation, they gradually decrease in entropy, creating apparent violations of the second law that are resolved only when quantum information theory is taken into account. These developments suggest that our understanding of entropy and the arrow of time might be incomplete in ways that are directly relevant to time travel scenarios. If information can be preserved in quantum systems in ways that violate classical thermodynamics, then perhaps time travel paradoxes can be resolved through similar quantum information effects that preserve overall consistency while permitting apparent local violations of entropic principles. The cosmological perspective adds yet another layer of complexity. If the universe is infinite in extent, then it contains regions in all possible entropy states, including regions where entropy appears to decrease with time due to statistical fluctuations. Time travelers might be able to navigate between these regions, moving from areas where entropy increases toward the future to areas where it increases toward the past. The apparent paradoxes would be resolved by the vast statistical properties of an infinite universe rather than by changes to fundamental physical laws. As we gently contemplate these intricate relationships between entropy, information, and temporal direction, we begin to see that time travel paradoxes are not isolated puzzles, but reflections of deep connections that run throughout physics. The arrow of time that governs our daily experience, the direction in which entropy increases and causes precede effects, creates the very context within which temporal paradoxes become meaningful. Understanding how time machines might operate requires understanding how they would interact with these fundamental thermodynamic currents that flow through the fabric of spacetime itself. As our exploration drifts toward its gentle conclusion, we turn our attention to the possibility that causal loops and time-like relationships might already exist in nature, woven into the very fabric of physical law and cosmic structure. While dramatic time travel scenarios capture our imagination, the subtle presence of temporal loops and self-causing relationships might be far more common than we realize, existing at scales from the quantum to the cosmological. At the quantum level, the relationships between cause and effect become beautifully complex. Virtual particles, those ephemeral fluctuations in the quantum vacuum we discussed earlier, exist in states where their creation and annihilation events are intimately connected across time. A virtual photon might mediate the electromagnetic force between two electrons, carrying information about their interaction backward and forward through time in ways that blur the classical distinction between cause and effect. The delayed choice quantum eraser experiments, first proposed by physicist John Wheeler, demonstrate even more dramatic quantum temporal relationships. In these experiments, the decision about how to measure a photon can retroactively determine the photon's behavior at an earlier time, as if information about future measurements travels backward to influence past events. While these effects can be understood within standard quantum mechanics, without invoking literal time travel, they reveal a universe where the temporal relationships between events are far more subtle and interconnected than classical physics suggests. Quantum entanglement creates correlations that transcend spatial and temporal boundaries in ways that Einstein famously called spooky action at a distance. When two particles become entangled, measuring one instantly determines the state of the other, regardless of the distance separating them. Some interpretations of quantum mechanics suggest that these correlations might also transcend temporal boundaries, creating entanglements between events at different times that appear causally disconnected from a classical perspective. The Wheeler-DeWitt equation, which attempts to describe the quantum state of the entire universe, suggests that time itself might be an emergent property rather than a fundamental dimension. In this timeless formulation of quantum gravity, the universe exists as a single, eternal quantum state that encompasses all possible histories and futures simultaneously. What we experience as the flow of time might be a perspectival effect that arises when conscious observers extract classical information from this timeless quantum state. Moving to larger scales, general relativity reveals that massive rotating objects drag spacetime along with their rotation, creating effects known as frame dragging or the Lense-Thirring effect. Near rapidly spinning black holes, this frame dragging becomes so extreme that spacetime itself rotates, creating closed time-like curves in the immediate vicinity of the black hole's ergosphere. While these curves exist only in regions where the gravitational fields are extraordinarily strong, they demonstrate that nature routinely creates the geometric conditions necessary for time travel. The cosmic microwave background radiation, that faint afterglow of the Big Bang that fills all of space, carries within its patterns the seeds of all future cosmic structure. The tiny fluctuations in temperature and density, encoded in this ancient light, determined where galaxies would form, where stars would ignite, and ultimately where planets and life would emerge. In a very real sense, the cosmic microwave background contains information about events that wouldn't occur for billions of years, creating a causal loop that stretches from the universe's infancy to its mature structure-filled present. Some cosmological models suggest that the universe itself might exist in a kind of causal loop. In cyclic cosmologies, the universe expands from a Big Bang, evolves for billions of years, then contracts back to a big crunch that becomes the Big Bang of the next cycle. Information and structure from one cosmic cycle might be preserved through the bounce and influence the development of the subsequent cycle, creating causal relationships that span multiple universe lifetimes. Even more speculatively, some theories propose that the fundamental constants of nature, the strength of gravity, the mass of the electron, the speed of light, might be determined through anthropic selection, effects that create causal loops spanning multiple universes. If conscious observers can only exist in universes with constants that permit the formation of stars, planets, and complex chemistry, then the existence of observers retroactively selects for the very physical laws that made their existence possible. Consciousness becomes both the product and the selector of physical law, creating a cosmic bootstrap paradox that encompasses the entire structure of reality. The emergence of life itself can be understood as a process that creates increasingly complex causal loops and self-referential structures. Biological systems maintain their organization by consuming energy from their environment and using it to reproduce their own patterns. DNA contains information about how to build the very molecular machinery that reads and copies DNA. Consciousness arises from neural processes that can observe and modify their own operation. Each level of biological organization creates new types of causal loops and self-causing relationships. Cultural evolution adds another layer of temporal loops to the mix. Ideas, technologies, and social institutions evolve through processes where the future influences the past in subtle but powerful ways. The anticipation of future technologies drives present research and development. Cultural values and beliefs shape the questions that scientists ask and the problems they consider worth solving. The future state of knowledge influences the present growth of knowledge through feedback loops that operate across generations. Language itself exists in a kind of causal loop with consciousness. We use language to think and communicate, but language also shapes how we think and what we can conceive. The words and concepts available to us constrain and enable our thoughts, while our thoughts drive the evolution of language. Meaning emerges from the interaction between minds and linguistic structures in patterns that are simultaneously cause and effect. These natural causal loops suggest that the temporal paradoxes we've been exploring might not be exotic violations of natural law, but expressions of deep principles that operate throughout nature. The universe appears to be constructed from self-referential, self-causing patterns at every scale, from quantum processes to cosmological evolution. The dramatic time travel scenarios of science fiction might simply be amplified versions of processes that are already woven into the fabric of reality. Consider how evolution itself operates through temporal loops that span millions of years. Random mutations occur in the present, but their survival depends on future environmental conditions and selection pressures. The genetic changes that persist are those that prove adaptive in circumstances that haven't yet occurred. In a very real sense, the future fitness landscape reaches backward through time to influence which mutations survive and reproduce. Evolution becomes a process where the future selects the past, where effects reach backward to choose their own causes. The development of scientific theories follows similar patterns. New ideas emerge from the existing framework of knowledge, but their acceptance depends on future experimental tests and theoretical developments. The theories that survive are those that prove useful for making predictions and generating new insights. The future utility of an idea influences its present acceptance, creating causal loops where the consequences of knowledge determine the knowledge itself. These patterns suggest that causal loops might be fundamental features of any complex, self-organizing system. Wherever information can flow backward through feedback mechanisms, wherever the future state of a system influences its present behavior, we find the essential structure of temporal paradoxes. The difference between these natural loops and science fiction time travel might be simply one of degree rather than kind. The holographic principle in physics proposes that all the information contained in a volume of space can be encoded on its two-dimensional boundary. This principle suggests that the interior and boundary of a region are fundamentally equivalent ways of describing the same physical reality. Applied to time, this might mean that the entire history of a temporal region, from past to future, is somehow encoded in its temporal boundaries, creating a kind of temporal holography where past and future exist simultaneously in the present moment. Recent developments in quantum gravity have revealed even more subtle connections between information, geometry, and temporal relationships. The ADS/CFT correspondence, a remarkable duality discovered in string theory, shows that certain quantum field theories in curved spacetime are mathematically equivalent to quantum gravity theories in higher dimensional spaces. This correspondence suggests that what we experience as temporal evolution in one theory might be seen as static geometric relationships in the dual theory, revealing deep connections between time, space, and information that transcend our usual categories. These discoveries point toward a universe where the boundaries between cause and effect, past and future, observer and observed, are far more fluid than our everyday experience suggests. Causal loops, rather than being exotic violations of natural law, might be expressions of the deep interconnectedness that characterizes reality at its most fundamental level. The temporal paradoxes of time travel become windows into this hidden interconnectedness, revealing aspects of reality that are normally invisible to our linear temporal perspective. As we approach the gentle culmination of our journey through temporal paradoxes, we find ourselves confronting the deepest philosophical questions that time travel scenarios illuminate. What is the nature of change itself? Do events actually become real, transitioning from possibility to actuality, or do they exist eternally in the static structure of spacetime? How do time travel paradoxes challenge our most fundamental assumptions about becoming, existence, and the passage of time? The philosophical tradition offers several perspectives on these questions. The eternalist view, which aligns closely with the block universe interpretation we explored earlier, suggests that all moments of time exist with equal reality. Past, present, and future events are equally actual, equally existent, spread out across the temporal dimension like locations in space. In this view, change is not the coming into being of new events, but simply the relationship between different temporal locations. Change becomes analogous to spatial variation, just as a road changes from asphalt to gravel without either surface being more real than the other. Time changes from past to future, without any moment being more actual than any other. This eternalist perspective dissolves many temporal paradoxes by denying that time travel involves changing the past. If all moments exist eternally, then time travel is simply a matter of navigating to different temporal locations. The time traveler who prevents their grandfather's death doesn't alter a previously existing event. They simply visit a temporal location where that death doesn't occur. The paradox disappears because there was never a single, definitive timeline to be changed. But eternalism creates its own puzzles about the nature of experience and agency. If all moments exist equally, why do we experience the present as somehow special or privileged? Why does consciousness seem to flow from past to future rather than existing simultaneously at all temporal locations? The eternalist must explain away our most direct and immediate experience, the feeling of temporal becoming, as some kind of systematic illusion. The presentist alternative suggests that only the present moment truly exists. The past has ceased to be real, and the future has not yet become actual. Change involves the genuine coming into being of new events and the passing away of old ones. In this view, time travel to the past becomes literally impossible because there is no past to travel to. The grandfather paradox is resolved through impossibility rather than consistency, but presentism faces severe challenges from special relativity. If only present events exist, which events count as present? The relativity of simultaneity shows that different observers disagree about which distant events are occurring now, making it impossible to define a universal present moment. Presentism seems to require a privileged reference frame that violates the fundamental principles of relativity theory. A third philosophical position, sometimes called the growing block theory, attempts to combine insights from both eternalism and presentism. This view suggests that the past and present exist, but the future remains genuinely unreal until it comes into being. The universe grows moment by moment as new events transition from possibility to actuality. This perspective preserves the reality of temporal becoming while accommodating the insights of relativity theory about the past. The growing block theory creates interesting possibilities for time travel scenarios. Travel to the past would be possible because past events genuinely exist, but travel to the future would be impossible because future events haven't yet become real. This asymmetry matches our intuitive sense that the past is fixed while the future remains open. But it creates new puzzles about exactly when and how events transition from unreality to reality. Time travel paradoxes illuminate the strengths and weaknesses of each philosophical position. The grandfather paradox seems to support presentism by showing the absurdities that result from treating the past as real and changeable. But the block universe resolves the paradox by denying that change involves the replacement of one reality with another. Bootstrap paradoxes suggest that some aspects of reality might be self-creating, existing in temporal loops without ultimate origins, challenging all three philosophical positions to account for self-causing events. The many worlds interpretation offers a fourth perspective that transcends the traditional debate. If all possible timelines exist simultaneously in parallel branches of reality, then questions about which events are really occurring become ill-defined. Every possible version of events exists in some branch of the multiverse, making the distinction between reality and possibility meaningless at the fundamental level. Time travel doesn't change reality. It navigates between different branches of an infinitely complex multiverse where every story is simultaneously true. This multiverse perspective suggests that the problem of temporal paradoxes might arise from inappropriately applying concepts like change and reality to structures that transcend these categories, just as asking about the color of Wednesday or the weight of justice reveals conceptual confusion rather than interesting facts. Asking whether time travel changes the past might reveal limitations in our conceptual framework rather than deep truths about temporal relationships. Recent developments in physics suggest even more radical possibilities. Some interpretations of quantum gravity propose that spacetime itself might be emergent from more fundamental structures, possibly networks of quantum entanglement or computational processes. In these approaches, time and causality would be approximate descriptions that apply only at certain scales or in certain limits, like temperature and pressure emerge from microscopic molecular motions in thermodynamics. If spacetime is indeed emergent, then the temporal paradoxes we've been exploring might be artifacts of applying temporal concepts beyond their domain of validity. Just as asking about the temperature of individual atoms reveals a category error, asking about causality and temporal sequence in regimes where spacetime breaks down might reveal the limitations of our temporal concepts rather than fundamental contradictions in the laws of physics. These perspectives point toward a radical reconceptualization of time, change, and existence itself. Perhaps the temporal flow we experience is neither fundamental nor illusory, but something more complex, a feature of how conscious systems extract classical information from quantum substrate, or how local observers perceive global geometric relationships in higher dimensional spaces. The study of time travel paradoxes thus becomes a probe into the deepest structures of reality, revealing aspects of existence that our everyday concepts struggle to capture. They force us to question not just our understanding of time, but our understanding of what it means for anything to exist, to change, or to become real. In pushing our concepts to their breaking point, temporal paradoxes open windows into possibilities that might require entirely new ways of thinking about the nature of reality itself. As consciousness navigates these conceptual territories, we find that time travel paradoxes are not just puzzles for physicists, but fundamental questions about the nature of experience, existence, and the relationship between mind and reality. They remind us that our most basic categories of thought, time, causality, identity, existence, might be far more provisional and limited than we typically assume. In contemplating the possibility of temporal loops and causal reversals, we catch glimpses of a universe that is far stranger, more subtle, and more beautiful than our linear temporal experience might suggest. As we drift toward the close of our gentle exploration through the landscape of time travel paradoxes, let us settle into quiet contemplation of what these strange and beautiful puzzles reveal about the nature of existence itself. We have journeyed together through territories where cause becomes effect, where information emerges from nowhere, where consciousness navigates impossible loops through the fabric of spacetime. Now, in the soft twilight of our investigation, we can rest in the profound mystery these paradoxes illuminate. There is something deeply peaceful about confronting the limits of human understanding, about encountering questions so fundamental that they reveal the provisional nature of our most basic assumptions about reality. Time travel paradoxes don't simply challenge our physics. They challenge our entire conceptual framework for understanding existence, causality, and the relationship between mind and cosmos. In doing so, they invite us into a state of philosophical wonder that transcends the merely intellectual and touches something deeper in the human experience. Consider how these paradoxes transform our relationship with time itself. In our everyday experience, time feels like a river carrying us inevitably from past toward future. We experience regret about missed opportunities, anxiety about uncertain outcomes, and the poignant recognition that each moment once lived can never be recovered or revised. But the temporal loops and causal reversals we've explored suggest that this linear experience might be just one way of experiencing a far richer temporal reality. If bootstrap paradoxes are possible, then some aspects of existence might be genuinely self-creating, pulling themselves into being through the mysterious loops of cause and effect, the musical composition that teaches itself across generations, the scientific theory that proves itself through its own implications, the consciousness that observes itself into existence. These scenarios point toward a universe where creativity and discovery might be more fundamental than we imagine. Woven into the very structure of spacetime itself, the many worlds interpretation offers its own form of cosmic comfort, suggesting that every possible story finds expression somewhere in the infinite branches of quantum reality. Every choice you didn't make, every path you didn't take, every word you didn't speak, all exist with equal reality in parallel timelines. The regrets and what-ifs that populate human experience become transformed into a celebration of infinite possibility, a recognition that all stories are told somewhere in the vast library of the multiverse. Even the grandfather paradox, that most troubling of temporal puzzles, reveals something beautiful about the nature of existence. It suggests that reality possesses a kind of self-consistency, a natural tendency toward logical coherence that transcends our ability to engineer contradictions. Whether resolved through many worlds branching, quantum consistency effects, or chronology protection mechanisms, these paradoxes reveal a universe that seems to protect itself against logical chaos, maintaining its own deep harmony through mechanisms we're only beginning to understand. The quantum foundations of reality add their own layer of mystery and wonder. At the deepest level we can currently probe, the universe appears to exist in superposition states, with all possibilities present simultaneously, until the moment of observation collapses them into definite outcomes. Perhaps consciousness itself plays a fundamental role in this process, serving as the agent that transforms possibility into actuality through the mysterious act of awareness. We might be far more intimately connected with the basic structure of reality than we realize, participating in the ongoing creation of existence through every moment of conscious experience. The thermodynamic arrow of time reminds us that we exist in a universe of exquisite impermanence, where every moment represents an irreversible step in the cosmic evolution from order toward chaos. Yet within this universal tendency toward entropy increase, pockets of extraordinary organization arise, stars that forge heavy elements, planets that develop complex chemistry, life forms that build intricate structures, consciousness that contemplates its own existence. We are temporary eddies in the entropic flow, brief organizational miracles that emerge from and return to the cosmic sea of randomness. Time travel paradoxes reveal that even this apparently fundamental arrow of time might be more flexible than we assume. In regions of extreme curvature, near rotating black holes, or within wormhole networks, the usual relationship between cause and effect might break down entirely. Time might flow backward, information might exist without origins, and consciousness might encounter versions of itself from different temporal epochs. The universe appears to be far more permissive of temporal strangeness than our everyday experience suggests. Perhaps most remarkably, these paradoxes suggest that the universe might be fundamentally self-referential, composed of structures that create and sustain themselves through loops of cause and effect that span dimensions we can barely imagine. From quantum processes, where virtual particles mediate their own interactions, to cosmological cycles, where the universe creates the conditions for its own rebirth, reality appears to be constructed from patterns of self-reference and self-causation that mirror the deepest structures of consciousness and awareness. As we contemplate these mysteries in the quiet darkness of approaching sleep, we might find comfort in recognizing that we are part of something far grander and stranger than our individual perspectives can encompass. We exist as temporary patterns in a cosmic dance of matter and energy, information and entropy, possibility and actuality, that spans scales from the quantum to the cosmological. Our consciousness, with its peculiar ability to experience temporal flow and contemplate its own existence, might be one of the universe's ways of knowing itself, of exploring the implications of its own strange and beautiful structure. The time travel paradoxes we've explored together remind us that reality is under no obligation to conform to our intuitions or satisfy our need for simple explanations. The universe appears to be far more mysterious, more subtle, and more wonderful than any single perspective can capture. These paradoxes invite us to hold our understanding lightly, to remain open to possibilities that transcend our current conceptual frameworks, and to find joy in the ongoing mystery of existence itself. In the end, perhaps the greatest value of contemplating time travel paradoxes lies not in solving them, but in allowing them to transform our relationship with uncertainty, mystery, and the unknown. They remind us that we inhabit a cosmos where the impossible might be routine, where logic and paradox dance together in patterns too complex for any single mind to fully comprehend, and where consciousness itself might be the universe's most profound and mysterious creation. As we prepare to rest in the gentle embrace of sleep, we can carry with us the recognition that we are part of a reality far stranger and more beautiful than we typically imagine. The time travel paradoxes that have guided our exploration tonight are not just abstract puzzles for physicists and philosophers. They are windows into the deep mystery of existence itself, invitations to wonder, opportunities to glimpse the profound interconnectedness that underlies all appearance of separation and sequence. In the quiet spaces between sleeping and waking, between one moment and the next, between past and future, we might sense something of the timeless awareness that witnesses all temporal flow, all causal relationships, all the apparent paradoxes that arise when consciousness encounters the deepest structures of space and time. This awareness, which exists somehow outside the flow of time while being intimately present in every moment, might be the ultimate resolution of all temporal paradoxes, not through logical solution, but through the recognition of our fundamental unity with the cosmic mystery we seek to understand. Let these gentle reflections carry you into peaceful sleep, secure in the knowledge that you are part of a universe far more wonderful than any paradox could diminish, far more mysterious than any explanation could contain, and far more interconnected than any sense of separation could ultimately maintain. In contemplating the impossible loops and causal reversals of time travel, we have touched something eternal, not a solution to the mystery of time, but a deepening appreciation for the mystery itself, and our extraordinary privilege in being conscious witnesses to its endless unfolding. Rest well in the embrace of cosmic mystery, knowing that whether time flows forward or backward, whether causality loops back upon itself, whether consciousness creates reality or reality creates consciousness, you are an integral part of the vast, beautiful, ever-evolving tapestry of existence that encompasses all possibilities, resolves all paradoxes, and embraces all forms of awareness in its infinite, eternal dance through the dimensions of space and time. Sweet dreams, fellow traveler through the mysteries of time. May your rest be peaceful, your dreams be filled with wonder, and your morning awakening carry the gentle wisdom that flows from contemplating the deepest questions that consciousness can pose to itself about the nature of existence, causality, and the strange, beautiful loops through which reality creates and knows itself across all the dimensions of space and time.